Students, now once again we are going to revisit irrational numbers. Already you learnt about irrational numbers in your previous class. So an irrational number is a number which cannot be written in the form of p by q, where q is not equal to 0, where p and q are integers. The examples for irrational numbers are root 2, root 3, root 5, then root 7, pi value. All these are the examples for irrational numbers. Today we are going to learn a contradiction method. Proof by contradiction method. What do you mean by contradiction? Contradiction means it is indirect proof. Contradiction means indirect proof. Now, theorem 1.3. So theorem 1.3 states that if P be a prime number, if P divides A square, then P divides A also. So here proof is not required. Proof will not be asked in the board exam. Only the statement is important. That is, if P is a prime number, P is a prime number which divides P divides A square, then P divides A also. A is an integer, a positive integer. If P divides A square, then P divides A also. Now using this statement we are going to prove the irrationality of the numbers. That is, prove that root 2 is an irrational number. While proving this, you need to follow 4 steps. What is it? First one, you have to assume the statement as false. For example, prove that root 2 is an irrational number. You have to assume it as rational number. That means you have to assume this statement to be false. Then the second step is proceed with the proof. Proceed with the direct proof. And the third step is come to contradiction, saying that this is not possible because of our wrong assumption. Then last step is, that is, conclusion. So now the first theorem we are going to learn, that is, let P be a prime number. If P divides A square, then P divides A also. So this theorem will apply in this proof. Example, the first example is prove that root 2 is irrational. Now we are going to prove that root 2 is irrational. You know that it is irrational. Now we are using the first statement here. Let us assume to the contrary. Let us assume to the contrary that root 2 is rational. Root 2 is rational. We are using false statement here. So let us assume that root 2 is rational. You know that rational number can be written in the form of P by Q, where P and Q are integers and Q is not equal to 0. So that here we assume that root 2 is rational. So you can write root 2 as A by B, where A and B are co-prime, and B is not equal to 0. A and B are co-prime. Now, cross multiply. B root 2 equals to A. Now, square it on both the side. So, you will get B square into 2 equals to A square. On squaring on both the sides. Squaring on the both sides. So squaring on both sides, you will get 2b square equals to a square. It means that, see here, It says that 2b square equals to a square. Therefore, 2 divides a square. 2 divides a square. So 2 divides a also because of theorem. Because of theorem 1.3. So 2 divides a square. So 2 divides a also. Now we'll take one more integer c. So let us take integer c. Integer c. Integer c such that so take one more integer c such that a equals to 2c. Take one more integer c such that a equals to 2c. Now again you square it on both the sides. What will get? A square equals to 4 square. Squaring on both sides. So squaring on both the sides you will get a square equals to 4 square. 4c square. What is a square? A square is 2b square. 2b square equals to 4c square. So 2 ones are 2 twos are. So b square equals to 2c square. It means that 2 divides b square. 2 divides b also. 2 divides b square, 2 divides b also. It means that both a and b have common factor 2. B has common factor 2 and here a also factor 2 is common. So both a and b are having common factor 2. It means that, see here, a and b are co-prime. Co-prime means what? They do not have any common factor other than 1. But here two common factor, this 2 is the common factor for both a and b. It means that a and b have common factor 2. That means 2 is the common factor for both. 2 is the common factor for both A and B, but this contradicts the fact that A and B. See here, our incorrect assumption. See, this contradicts the fact that our assumption is wrong because we assumed that it as a rational. But we are getting here B as a common, this is 2 as a common factor for both A and B. So this contradiction arises because of our wrong assumption saying that root 2 is rational. Therefore, root 2 is not rational. This is irrational number. Once again, I will repeat. See here, let us assume to the contrary that root 2 as rational. Rational means anyhow we'll write in the form of a by b where a and b are co-prime and b is not equal to 0. Once again I'll repeat, co-prime are the prime numbers which are not having common factors other than 1. Okay. Now cross multiply b root 2 equals to a. On squaring on both the sides, b square into 2 equals to a square. So a square equals to 2b square. That means 2 divides a square, 2 divides a also because of theorem. Theorem 1.3. P is a prime number. So P divides a square where P divides a where a is a positive integer. Okay. Now we take one more integer c where a equals to 2c. Then square it on both the side. You will get a square equals to 4c square. Then simplify. You will get b square equals to 2c square. But here you see 2 divides b square and 2 divides b. Now here both a and b have common factor 2. So this contradiction has arisen because of a wrong assumption, that is root 2 is rational. Therefore, root 2 is irrational. I hope you understood this. For all the proofs, you have to write the same steps. Whether you are proving root 2, root 3, root 5, root 7, all the steps are same. Understood? Okay. Now next we take one more example. Example 2. Example 2. Prove that 3 plus root 5 is irrational. So first step is, let us assume to the contrary that 3 plus root 5 is rational. Let us assume to the contrary that 3 plus root 5 is rational. So rational numbers can be written in the form of P by Q or A by B. So 3 plus root 5 equals to A by B, where A and B are co-prime and B not equal to 0. Yes. Then now see here, root 5 equals to A by B minus 3. So shift 3 to right side. So root 5 equals to A minus 3B by B. Now see here in this equation, A and B are co-prime, positive integers. Okay. Now A minus 3B by B, it is a rational number. But here LHS, it is an irrational numbers. Rational is equal to irrational. Is rational is equal to irrational? No, this is not possible. Now, see here, A and B are integers, they are co-prime. So, A minus 3B by B is a rational number and root 5 is irrational number. Now, but this contradicts the fact that the given number is not a rational number, it is an irrational number. So, this RHS is rational, but LHS is irrational here. Why? Because A and B are positive integers. Now, is rational is equal to irrational? Is it possible? No, this is not possible. But this contradicts. So, if this is rational, then this is also rational, right? So, A minus 3B by B is a rational. Then root 5 is also rational. But this contradicts the fact that root 5 is not rational. It is an irrational number. Therefore, this contradiction has arisen because of our wrong assumptions saying that 3 plus root 5 is rational. Therefore, we conclude that 3 plus root 5 is irrational. So, we conclude that 3 plus root 5 is irrational. I hope you understood this sum. Okay. The next concept is revisiting rational numbers and their decimal expansion. Rational numbers are numbers which can be written in the form of P by Q, where Q is not equal to 0. Now, once again, we'll write this rational number in the decimal expansion without division. Without division. So, for this first theorem, that is theorem 1.6. Theorem 1.6, which states that if x be a rational number which terminates the prime factorization of, now see here, if x is a rational number of the form P by Q, where Q is in the form of 2 to the power n into 5 to the power m, then that rational number terminates. When a rational number p by q, where q is in the form of 2 to the power n into 5 to the power m, then that rational number terminates. For example, you take, for example, 3 by 8. So 3 by 8 can be written as 3 by 2 to the power 3. Now, here what is q? This is q and this one is p. Now we have to check whether it's possible to write q in the form of 2 to the power n into 5 to the power m. Okay, now we'll try. See here. Now I will multiply both sides by 5q. Multiply both sides by 5 cube. Now you see here 3 into 5 cube is 125 and this is 2 cube into 5 cube, which is in the form of 2 to the power n into 5 to the power m, right? Now, okay. Now, so 5 3s are 15, 3 2s are 6 1s 7, 3 1s are 3, 375. Now, 2 into 5 to the power 3, right? So 3 to 75 divided by 10 to the power 3. So which is 375 by 1000. So 0.375. So without division we can write the decimal form of this rational number. See here 3 by 8. So here P is equal to 3, 8, Q is equal to 8. Now we have to check whether we can write this denominator in this form or not. So to write this you have to multiply 5 or 2 on both the sides and then simplify. So theorem 1.6 says that let x equals to p by q, let x equals to p by q be a rational number such that prime factorization of q is in the form of 2 to the power n into 5 to the power m, where n and m are non-negative integers, then x has a decimal expansion, which terminates. If q is not able to write in the form of 2 to the power n into 5 to the power m, then it is a non-terminating decimal expansion. That is the next theorem, theorem 1.7. Let x equals to p by q, where p and q are positive integers, and if q is not equal to 2 to the power n into 5 to the power m, then the decimal expansion of x is non-terminate decimal expansion. We'll take one more example. Second example. 2 by 14 or 15 will take. 2 by 15. Okay. 2 by 15. And I will try. So this is P and this one is Q. Now we have to write Q in the form of 2 to the power n into 5 to the power m. Okay. 2. So 15 is 3 into 5. 3 into 5. Now multiply both sides. See here. Is there any factor like 2 and 2? 5 is there already. So factor 2 is there? No. So is it possible to write in the form of 2 to the power n into 5 to the power m? Is it possible? Not possible. We'll cross check. 15 divided by 2 divided by 15. 0. Okay. Now So first we divide 15 ones are 50, right? Then 5, 50. Okay. 15 threes are 45. Again 50. 15 threes are 45. Again 50. So the decimal expansion of 2 by 15 is 0.13333. So 3 is repeating, recurring. So the decimal expansion of 2 by 15 is 0.1333. Non-terminating, recurring decimal expansion. Non-terminating, recurring decimal expansion. So the theorem 1.7 says that if x equals to p by q be a rational number such that prime factorization of q is not of the form 2 to the power n into 5 to the power m, then where m and n are non-negative integers, then x has a decimal expansion which non-terminating repeating decimal expansion. Non-terminating repeating decimal expansion. We'll take one more example. 987 divided by 10,500. 987 divided by 10,500. Now first we'll simplify this. So this is divisible. So divisible by, which number it is divisible? So this is divisible by, see here, 8, 8, 16, 17, 24. So divisible by 3 on both the side. So 3 3s are 9, 3 2s are 6, 3 9s are 27. Then 3 3s are 9, 3 5s are 15. So 3,500. Again it is divisible. See here. So which number it is divisible? Divide both the sides. 7. So which is divisible by 7. See 7 5s are 35. 7 5s are 35. Then 7. 7 4s are 28. 7 7s are 49. So 47 by 500. Now we have to check whether it is a terminating or non-terminating decimal expansion. So we have to check whether it is terminating or non-terminating. Now, so this can be written as 47 into 5 into 100. So 47, 5 into, so 100 can be written as 10 into 10, 10 square. So which is nothing but 47, 5 into 10 can be written as 2 into 5 whole square. So 47 divided by 5 into 2 square into 5 square, which is nothing but 5 cube into 2 square. Now multiply both side by 2. So you will get 7 2s are 14, 94, 4 2s are 8 plus 1 9 divided by 2 cube into 5 cube. So which is nothing but 94 by 2 into 5 whole cube. It is 94 by 10 cube. 10 cube means how many decimal place? 3 decimal place. So 94 by 10 cube. So which is 0.094. So Decimal expansion of this number is 0.094. So like this, without division, you can express the given rational number in decimal form. So the theorem, that is 1.6 and 1.7. 1.6 theorem says that if x equals to p by q is a rational number, if q is able to write in the form of 2 to the power n into 5 to the power m, q means that's a denominator, then only we can say that it is a terminating. If q is not able to write in the form of 2 to the power n into 5 to the power m, then it is a non-terminating recurring decimal expansion. I hope you understood this sum. So here we completed all the required concepts which are required for your board exam. So Euclid division lemma I will take at the end of this academic year. After completing all the portions, I will take all these cancelled portions. Okay, thank you students.